Hello everyone, welcome to our final ASHRAE workshop. Today we're going to be focusing on not a specific standard, but sort of a concept in general about building science. So if you'd like to turn on your video, you can. If you don't want to, you can leave it off because we will be recording. But we're going to have us start off with indoor comfort, and Adriana is going to start with that.
So I'm just going to give a quick info to the indoor environment and thermal comfort. So the ASHRAE 55 standard deals with the indoor environment and how thermal comfort affects building occupants. So thermal comfort is where building occupants are satisfied with the thermal environment. So things that people can control in terms of their thermal environment are their activity, their clothing, and then things that have to be designed within the building enclosure include the temperature, relative humidity, radiation, and air movement. Next slide.
Okay, so moving on to the outdoor environment, which is equally as important as the indoor environment. Basically, the outdoor environment is just concerned with the extreme temperatures and the relative humidity of the outdoors at a certain point in time. For example, in Toronto, we have -10 winters, pretty cold, and 10% relative humidity. And then in the summer, very much the opposite, we have 25 degrees Celsius temperatures and 70% relative humidity. Next slide. So basically, how do we combat this? Well, we look at heating degree days and cooling degree days. So essentially what a heating degree day is it quantifies the number of days a building needs heating. So if you look at the graph on the right, you can see that we have a kind of like a baseline, the orange line, that's just like the, I guess, steady temperature that you want to set for the building or the thing that you're going to measure against. And then you have all the temperatures that are externally happening. And in order to figure out how much you need to heat a building, you essentially just take that difference and use that in a calculation to help you better monitor how much heat is necessary. And then it's the same thing with cooling days. You basically are just taking the number of days that the building would need cooling based on a graph that you have of the days that are hotter than the indoor temperature that's desired. So basically, to calculate it, you just subtract the average monthly temperature from a base, which is usually around 18 degrees Celsius, and then you multiply that by the number of days in a month. So it's pretty simple. And then above or below heating or cooling is required for thermal comfort, because obviously you want a certain kind of relatively like body-like temperature in your space. So it's very important to know this calculation for energy demand. Next slide. Basically, the biggest thing when it comes to designing for the outdoors is designing for the climate. So you want to separate the indoor and outdoor conditions. That's basically the purpose. And then the weather is what's happening right now, and the climate is long-term trends. So for example, if you had a cold climate, enclosures would need to be sealed to not let air penetrate the building, and they'd need to be well designed to control temperature, moisture, and air movement, for example, like snow or rain. And then in a warm climate, you want them to be open and allow for natural flow, because in warm climates, there tends to be a lot of relative humidity, and you need to have air that can flow over these inner workings of a building, because you don't want them to grow mold and things like that. Next slide. The other thing that's really important when it comes to outdoor kind of effects on buildings is solar and building orientation. So in North America, we build a lot of our buildings facing south because it takes advantage of the solar heat gain, because in the afternoon there's a lot of sun facing from the south. And the other thing that's very important when it comes to building orientation is wind. Because wind patterns and wind roses can determine how temperatures and things like that affect the building, as well as precipitation. A good example is rain screens. So if you want to control the amount of rain that can penetrate its moisture into the building, you can make a rain screen, and allow for control of higher humidity levels in places that get a lot of rain, like rainforests and things like that. Next slide.
Buildings should be kept comfortable in order to maximize productivity inside. But this is becoming harder and harder due to climate change. As you can see from this graph, there is a steady change in the climate from that of a colder to a hotter one when we look at the average temperature. This is specifically relevant to building science because 25% of greenhouse gas emissions come from buildings. This leads to CO2 levels rising in the atmosphere, which in turn leads to more extreme weather events in the future. This is important because we need to ensure that for the future we design buildings accordingly so that they can, and retrofit existing buildings, to ensure that they can cope with these more extreme weather events and ensure that we can remain productive inside of the buildings.
And the next topic in building science is about air movement in buildings. And this consists of 3 different types, which are wind, mechanical, and stack. And wind is the first type, and it's basically pressure that's generated when wind is acting on a building. And the second one is mechanical, where air movement is essentially induced by flow from electric or manual fans. And the third one is stack effect on a building, which is caused by air movement due to pressure differences. And this is because warmer air is less dense than cooler air, so it rises to the top of the building. And during a cold winter day, this creates low pressure near the bottom of the building, where cooler air enters through doors and windows. And near the top of the building, warm air tries to escape in the building. And this is due to pressure differences, as you can see in the diagram to the right. And the opposite happens for a hot summer day, as you can see. And stack effect needs to be controlled properly, or else it would increase additional air loss and increase maintenance costs. And it will also cause moisture to enter the building, which causes bacteria and mold that would affect the building's occupants' health. And there's also a spot where the stack has no effect, and this is called the neutral pressure plane, where air doesn't come in or out. And the elevation of this is dependent on how much air leakage there is in the building. And in the end, stack effect is unavoidable, so it's best to take advantage of the wind patterns and plan accordingly. And that's it for air movement.
Okay, now I'm going to be talking a bit about designing walls of buildings because that's also important as well. So heat flows through buildings from warmer to colder temperatures. And it's important in colder climates like Canada right now. You need lots of insulation in your walls. And insulation is important due to their thermal resistance properties. So thermal resistance is defined as how much the material can resist heat flow, heat transfer. So you want these materials so that it can keep your indoor air climate, so like inside the building, warmer. And as you can see in the 2 pictures on the slide, so this is batt insulation, so the pink fiberglass stuff that you see. And these are very easily handled like insulation blankets. And they usually go in between frames within the walls. Next slide.
So also to design walls, we need to control the moisture that moves through the building. And moisture can move through enclosures by vapor pressure differences, air pressure differences, liquid capillary, adsorbed water, and free water. And what we're really trying to sort of go through is trying to, I guess, reduce the amount of water that does need to move through the building through these processes. Next slide. And why moisture is a sort of potentially a bigger concern is because of mold that can potentially grow in between your enclosures. Mold can cause decay of your materials, and it also can sort of affect the health of the occupants inside of a building by causing things like respiratory illnesses or even mental health. And the biggest sort of thing that we're looking for in terms of moisture in walls is condensation. And if you remember from a couple of presentations ago, we talked about how condensation occurs when your relative humidity reaches 100% or you're at a dew point. So basically, you can design walls to mitigate these effects. Next slide. And some solutions on how you can design a wall to reduce the or to control moisture control is making sure that if it has the potential to get wet, it also has the potential to get dry. And you can do this by using things like air spaces or low permeance membranes. And I guess especially that membrane should go on the warm side of the wall in Canadian climates, but that's very dependent on the climate that you're in. And you can also use things like rain screens or drip systems, as you can see in those pictures. And I believe Margot had mentioned them earlier as well. Next slide. Another type of movement that happens in walls is also the air movement. And the basic design principle with this one is making the building as tight as possible. And what that means is trying to sort of mitigate the amount of holes or just leakages that can occur, because air will want to move through that one a little bit more quickly. Typical types of materials that are used are either mechanically fastened or self-adhered. Self-adhered membranes are definitely better just because they just stick right to the building, but they are harder to put up, especially in windy conditions, because they kind of just stick onto each other, and then you've lost the seal that it can go onto the building. The biggest loss also occurs at joints and windows, or if you can think about bends, because if you're trying to make things as continuous as possible, those are probably going to be the hardest to sort of seal up. So solutions to deal with this would be keeping windows in plane. And what that means is not really having further sort of window sills and things like that, because that causes a thermal bridge, which basically just makes the building enclosure lose more heat through the structural members over there. You can also add sealants on joints, which sort of just mold into the space and block off any air leakages. And you should also keep barriers as continuous as possible, as mentioned before. Some testing that you can do to make sure that your enclosures are properly sealed would be the blower door test, which basically just pushes air through the building, and it kind of gives you a reading to say how much air you're losing, or smoke test, which you can put directly on the leakage point, which shows you if smoke is getting through it or not.
So now we'll be talking about solar radiation in buildings, which is very important. So the amount of daylight per day is dependent on its orbit and the tilt of the Earth's axis. The position of the sun is determined by the solar azimuth. You can see on the diagram, and the solar altitude, but the thing we are most concerned about actually is the intensity of the solar radiation, which actually varies with the distance from the sun to the Earth. Next. The radiation can reach the Earth by a variation of different ways. You can have a direct beam radiation. From the diagram, you can see it there. You can also have scattered radiation, reflected radiation, and then the sum of all three is the total clear sky radiation. And so solar radiation is important because it leads to solar heat gain through windows of old buildings. And to reduce heating load in the winter, you need to reduce the solar heat gain or increase the cooling load in summer. Solar gains can also occur through opaque windows. This comes in the form of shortwave gains from irradiance and long-wave gain from the environment. Shading can occur due to solar geometry, which will have a large impact on solar gains. For example, roof overhangs, which prevent higher angle solar radiation in the summer, as you'll see from the next slide. So as you can see from the diagram, the roof overhang is just a little bit over the top. An efficient building would make use of the solar heating with large windows and oriented to be exposed to the sunlight. This is especially useful in the winter when the sun is lower, and so the windows are more exposed and for longer during the day. This type of design is therefore good for a heating dominant climate. The roof overhang can also be used to block the sun when it is higher in the sky in the summer. This leads to decreased cooling loads in the winter as the roof overhang limits solar gains. This type of design is therefore good for cooling dominant climates. Next slide. I guess that's it.
I'm going to end the recording here. So thank you so much to everyone who's watching this. And thank you so much for attending and watching our workshops that we kind of tested out this year due to everything being online. So we're really appreciative and thankful that you took interest in these topics. So I'm just going to end the recording here.